We've just introduced the basic definitions. We defined the age itself, theta, we defined real-time t, and we defined the internal and external age distributions I and E of theta. What we want to look at now is ways to estimate these internal and external age distributions. And to do that, we're going to consider some space, like a reactor space. And we're going to consider the flow into that space, first of all. So we are being fed with some stream here. So for instance, if that's just water flowing into the system, we might break up this inlet stream in terms of time. So if we take 1 second intervals here, we can say that material further up this pipeline will only enter, perhaps that's 5 minutes in the future. Material here might enter 4 minutes, 3 minutes, and so on. So we can take these 1 minute intervals along this pipeline, and that identifies for us different cohorts of fluid elements. So the idea of cohort is it's a group in the population, a subgroup of the population, and the subgroup is understood to be different to the other groups just in terms of the time at which it has entered the space. So this cohort, for example, is going to enter the space, and of course when it does, it will undergo some kind of mixing here. So we aren't at this stage going to prescribe the type of mixing. We aren't going to say it's perfect or plug flow or anything like that. We're just going to say we know generally this packet of fluid elements is going to break up, and we'll get fluid elements going here and here and here, and they'll be progressing on their own individual paths towards the exit point. So some might circulate for a while and so on. So we discussed that sort of thing before. So these fluid elements are progressing along their own paths to the exit point, but these have all come from this particular cohort. And of course there are other fluid elements in this reactor, so you will have other molecules there of the same type, but we are drawing them differently just because they have entered at different times. And we are, of course, interested in the age distribution inside the reactor and at the exit point, right, our I and E. But the difficulty for us is that we cannot distinguish this any fluid element from any other. So we said, for instance, this was water coming in. Now, if you look at that reactor, you will see a vessel full of water. How can you distinguish one molecule from the other? You really can't, right? So the useful concept to try to create this distinction is the tracer. So at some point we may inject something into our entry stream. So if at some instant in time we inject, let's say, salt into this entry stream here, then we are effectively tagging a specific group. So out of all the water that's entering that reactor, when we inject salt quickly into our entry stream, we are effectively tagging the water elements, the molecules of water that are entering the reactor at that time. It's a little bit incorrect what I'm saying. You can't really say you are tagging a molecule, but we are just saying that that salt is entering at the same time, at least, as the molecules of water in that system. Now, if that salt mixes well with the molecules of water, then that salt is going to do what we call uniform suspension. So that salt is going to progress through the system in the same way as the other water molecules. So if we were to measure at the exit point how that salt concentration is going to vary with time, then that will give us some idea about the mixing at the exit, or the age distribution at the exit. So, well, we haven't made that connection yet, but let's just say we can measure the concentration as a function of time, and so we'll at some point start to see salt appearing at the exit, and that's an indication of how long the salt has spent in there. So if we analyze this pattern, we are hoping to identify something about the nature of the mixing there. So let's say we are now interested in the fluid elements that have been in the reactor between 10 minutes and 11 minutes. So let's say we are interested in the specific range 10 to 11 minutes. So we want to know what's the fraction that will spend that period of time in the reactor. Right, so let's say to do that, we then perform this kind of experiment. We inject salt into the reactor. So let's say we inject at 12 o'clock and we observe at the exit point. We measure this kind of curve, this concentration with time. And there are various ways to do this. We might use a conductivity meter, right? Salt affects the conductivity of the fluid that's passing through. So we could calibrate this, the conductivity for concentration, and we can translate it back and get concentration as a function of time there. So we've injected at 12 o'clock, and we are interested in this specific age range. Now, we've injected the salt, and that's tagged a specific cohort of the water that's entering. And so when we ask for this specific age range, we will start to see those fluid elements at the time range 12:10 to 12:11. Right, and sorry, I'm using the my time notation is like this. This is not mathematical. It's not 12.1. This is 12:10. Maybe I should write it more correctly as the standard form. Right, so that's the actual time range that we're interested in. So when we look here on our concentration time graph, this is the group of fluid elements of interest to us. So if we can gauge the number of moles of salt that exited at that time, then we can say that is the amount of salt that has exited having that age, having spent that amount of time in the reactor. And of course we can do this quite easily. Number one, we anticipate that we were fixing the flow rate through the system. So there's some flow rate, some volumetric flow rate here. So cubic meters per, I guess we're dealing in minutes, so let's stick to that, cubic meters per minute. So we can say that the number of moles of salt that exited in that range, so moles of salt in of the age range theta is 10 to 11 minutes. The number of moles of that is going to be the concentration of the salt at that time, and that is at the time, let's say 12:10, and then if we multiply by the volumetric flow rate, right, we assume this volumetric flow rate is fixed and steady. So concentration times flow rate here is going to give us molar flow rate, so that's a flow rate. Now, what must we multiply by to get the actual number of moles in this time range? Right? What do you multiply with over here? And maybe you want to pause this video and think about it for a few seconds. Okay, so if we think about what we have to multiply with over here, remember we are looking for the time range 10 minutes to 11 minutes. And we are saying we're going to start looking at the concentration at 12:10, right? We injected at 12 o'clock, so if we start looking at 12:10, then we are starting to look at elements of age 10 minutes. So if we want 10 minutes to 11 minutes, then of course it's going to take 1 minute for this range to flow into the reactor, right? 1 minute has to pass for this amount to leave the reactor. So we have to multiply here by 1 minute. That's our delta, delta theta or delta t. Right, so I would rather write that a little more generally as delta t here, right? And we can say delta t is 1 minute, because that's the range there. So if you look at this now, the units are correct. We've got concentration, moles per cubic meter. We've got here cubic meters per minute, and we've got minutes. So the product of all that is moles. So this is the number of moles of salt that will appear at the exit, right? This is the concentration at the exit. That's the number of moles of salt at the exit in the age range 10 to 11 minutes. Right, so that's quite a lot of progress. We now have a way to estimate the number of moles of salt that has spent this specific range of time in that reactor. Now remember, what we are really looking for is the fraction. Right, we had defined that E of theta, delta theta, is the fraction of fluid elements in the range theta to theta plus delta theta. So we want a fraction. This is a number of moles. So to get this to a fraction, we of course need to know the total number of moles. We want to divide this specific number of moles by the total moles that the total moles of salt. And there are a couple of ways to do that. We could first of all ask, well, how much salt did we put in here in the first place? Right, and even if we injected that, we can get the concentration perhaps in the syringe and look at the volume of the syringe, so there are ways to estimate it there. You could also say, well, if this reactor doesn't have any dead zones, then zones where fluid is just circulating without exiting. So if it doesn't have that, then all that salt must exit after a certain period of time. So if we follow this curve, when we see the concentration is approximately 0, we can say, well, all the salt must have exited by that time, and so we can just add up the number of moles across this whole curve here and say, well, that must be the total amount of salt that we had in there. And that's what we do. We can say the total number of moles, let's use a big N for that. Total number of moles is going to be the sum of all these intervals. So we can say we'll take the concentration at some specific time Ti and multiply that by the volumetric flow rate. So this is giving us the molar flow rate, and we multiply that with the change in time for these specific intervals I. So we are choosing intervals like we set intervals there. We are picking intervals, and then the I value specifies which interval we are looking at. So for a given interval, there's a given period of time. So each of these tells us the number of moles, and it's really at the exit point, so the number of moles at the exit point in that range. So we just add them all together, and that must be the total number of moles of salt. So the fraction we are looking for, then we can say E of theta delta theta is equal to the number of moles of a specific range, of that specific range. So that's going to be C, and you see here we've got time, right? And of course we just have to subtract this time from the injection time. So the injection time, the inlet time, was 12 here, so 12 o'clock, and we just subtract that from there, and we can get that to age. So we can say theta equals T minus T naught. So this is concentration for age theta, and then we have to multiply by the volumetric flow rate and multiply by the time interval delta T, and in this case delta T we are taking to be the same as delta theta. Remember, everything is getting older at the rate of 1 second per second. We are aging at the same rate at which time is passing. So we can write this as a delta T. In other words, d theta dt equals 1 is approximately the same as delta theta over delta T. Right, so delta T equals delta theta, and then we are substituting T for theta. and so that's the number of moles there. And then we want to divide this by the total number of moles, so we said add up for all intervals I for the concentration at the ith choice of age, and then we have to multiply that with the volumetric flow rate and the time interval delta theta I. So we can do some simplification here. First, let's cancel these delta thetas. So we've got in the numerator delta theta, and we've got a delta theta on the left hand side. And then we can also see here this volumetric flow rate can cancel in the numerator and denominator. So that's a different cancellation. That's there. And so we can say E of theta looks like C of theta divided by the sum over I C theta I, theta I, multiplied with delta theta I. And if you look in this denominator, this should immediately remind you of something, right? Take a second, let's just give you a second to shout out the name of this operation. Right, so this is the Riemann integral. Right, you can see you are adding over an interval. You've got a variable of some function, right? There's this function here, so you've got a function, you've got the variable of the function and a delta in that function, so this is nothing but an integration. Right, so just a quick reminder, your Riemann integral, if you were looking at the integral of y in x, then you could get that simply as the sum of y of x in delta x if you are considering specific intervals, right? The discrete form considering specific intervals like that. So that's a Riemann integral, so we can write this more simply as c of theta over the integral in c of theta. Right, and this is a beautifully simple result. If you look at this, it's saying that if I wanted the age distribution of the salt, right, admittedly this is all about the salt so far, so if I want the age distribution of the salt, all I need to do is inject some there, measure the concentration out there, and then take that curve and just divide by the area under that curve, right? This right here is nothing but the area under the curve. So I just take the curve, divide by the area under the curve, and that's giving me this function E of theta. Right, that's quite an incredible result if you think about it. It's saying that we can estimate the age distribution here from an extremely simple experiment like this. And in fact, we'll do a lot more with this experiment. We'll be able to use this experiment theoretically as well. So we have a simple means now of getting the exit age distribution. And of course, we said this was all for salt, but a condition that we imposed earlier on was to say, well, if we are regarding the salt as a kind of tracer, right? The salt, if it mixes well with the water, and if it's uniformly suspended in the water, then it's going to distribute itself in the same way that the water does. And so the age distribution of the salt is also going to be the same as the age distribution of the fluid element that we of the fluid that we are actually interested in. So we could have said ES there for salt. This is really salt, all this is salt, so you can go and correct everywhere for salt. And we are saying this is the same as the age distribution of the fluid that we are actually interested in. So that's how we can estimate an exit age distribution. We just apply a tracer, and we have to ensure that that tracer has the same characteristic as the fluid itself, and we can then measure the response of that tracer. So from the response of that tracer, from the concentration versus time of that tracer, we simply take the concentration profile itself, divide it by the area under that concentration profile, and that's going to give us this function E of theta. And we can also think about a few comments here. We can consider the units of this. So the units look like, so up here we've got moles per cubic meter, and down here we are integrating moles per cubic meter with respect to time. So the units down here look like moles per cubic meter times time. So this is going to be 1 over seconds. So the unit of E of theta is 1 over seconds, right? And remember, our requirement is that E of theta delta theta is going to be a fraction. And of course, a fraction is dimensionless. E of theta is 1 over seconds, and delta theta, that's units of time, so that's seconds. So you can see these cancel to give us a dimensionless quantity. So the units at least are dimensionally consistent as well. Right, so we now have a way of finding the exit age distribution, and that's quite specific. That's the age of the fluid elements in the exit stream, right? Because that's what we are measuring. We are measuring the concentration in this exit stream. We now need a way to relate this E of theta to I of theta, right? We expect that there should be some relationship between these two, right? After all, I of theta, the internal fluid elements, that's what's left over once we lose fluid elements in the exit stream. So perhaps there's some relationship between those two. So that's the next piece for us to develop.